Good afternoon to all of you. Let's start the session. We'll continue with Module 4, which is Transport Layer. Some of these things that we are going to study today, you have already studied in the lecture session. That's why there is a little bit of overlap between your CCNA session and what you study in the lecture. Okay. When you do your CCNA-2 and distributed network and CCNA-3, again, you will see some overlap, which is good. Repetition is always good, and it will drive away the concept in your mind and make it much more thorough. Okay, so let's start today's session. We'll be doing transport layer, which is your module 14. We will look at the main protocols that we have in transport layer. We will look at the concept of the whole overview of transportation of data, TCP, UDP, the main protocols, and how port numbers are used in both TCP and UDP. Okay, and we will look at also the concept of TCP communication, UDP communication, and how transport layer is also responsible for reliability and flow control. So let's get started. Transportation of data is what transport layer is mainly all about. Okay. It is responsible for the logical communication between the applications running on different devices. Okay, be it IP telephony device, be it smart TV, or be it a computer or a smartphone, and so on. Okay, it's always an interface between the application layer and your below layers, which is your network, data link, and physical layer. So if you look at a transport layer, it's the place where segmentation happens. Okay, it segments your data and sends it to the other layers, or it can also reassemble the segments that arrives. Okay. It also adds header information. It uses multiplexing, okay, so that you can send multiple data, okay, on the same network. If you look at your transport layer, the two main protocols that are used are TCP and UDP, something which you have studied in the lecture before. Okay, TCP is responsible for your FTP, HTTP, SMTP. Your UDP is responsible for your DNS and TFTP and so on. Okay, so with your network layer working with IP and your transport layer bringing to having protocols like TCP and UDP, you can have a proper communication taking place. Okay. Another aspect of your transportation layer, transport layer, is transmission control protocol. Okay, that TCP, it allows for proper communication. Okay, whereby the data that it's sent has got a proper acknowledgement. Okay, if there is no acknowledgement, it will retransmit the data when it comes to your TCP. Okay, and it doesn't matter if it comes in proper sequence or wrong sequence, it will arrange that sequence in the recipient. Okay. It also, as we studied, it also does flow control, as we will see. if the recipient cannot cannot receive the data with the speed that it is being sent, then the flow control can be adjusted. And that's also responsible by your transport layer. Another protocol besides the TCP that we have is the UDP. Unfortunately, UDP is a connectionless protocol. It follows the best effort delivery, and there is no acknowledgement. Okay, so the positive side of this, the upside of this is that it's very fast. Okay, you may lose data, but then the data transfer rate would be very fast. Okay, because it doesn't establish the connection first. It follows the best effort. UDP is necessary in places like when you're using voice over IP, okay, when you're using your domain name resolution, part of it works with your UDP, okay, it needs faster access, okay, whereas your TCP, your email works on that, and your actual web browsing by using the HTTP and HTTPS protocols is based on your TCP, okay. So certain applications would work better with UDP because you need low overhead, you need fast access, okay? It doesn't require acknowledgement, and it does not need to resend lost data, okay? Think about using your Skype, which is a voice over IP application, okay? That uses your UDP. Okay, before we go to UDP, let's start with TCP, okay? The main features: establish a session, make sure that the delivery is reliable. If the segments come in different numbers, arrange them again in the same order delivery, okay? Ensure that there's a proper flow control. Okay, if the recipient cannot access cannot receive the data, then you perhaps have to slow down the sending of the data. Okay, so the source can actually reduce the rate of data flow. Okay, again, I want to remind you all, we have studied this already in the lecture. Okay, we are just repeating as far as your CCNA-1 is concerned. You have to know this. So a TCP header is a stateful, first of all, a TCP header consists of, without the application data or the options, it consists of 20 bytes. That means if you look at the individual bits, it's 160 bits, okay? So 160 bits divided by 8, that would be 20 bytes, okay? When you talk about TCP, it's a stateful protocol, okay? That means it keeps track of the state of the communication session. That means, has the data been sent? Is it acknowledged? If yes, fine. If not, then send another one, okay? If you look at these 160 bits, source port 16 bits, destination port 16 bits. Then you have got sequence number, acknowledgement number, header, reserve, control bits, the window, the checksum, the urgent, and so on. Okay. So these are the different fields of your TCP header. Okay. What does the TCP do? It handles certain protocols. It's responsible for your HTTP, which allows you actually to browse and get information from the server. FTP to transfer files, okay? SMTP to push your mail from one location to another location. And SSH, your secure, it allows you to make sure that your data transfer is encrypted, okay? And just people who use packet sniffers, they won't be able to read your data, okay? So that is the whole idea of having TCP. With that, please adjust your microphone. Switch off your microphone so it doesn't disturb the class. Thanks. Now, what about UDP? Let's look at UDP. In UDP, it's not like TCP. The data has to be reconstructed exactly in the order that it is received. And once a segment is lost, it is not resent. If you're having a Skype conversation and one part of the conversation is garbled, that's it. It won't resend that, okay? There's no need for having a session establishment. That's why best effort, okay? And the sending is not informed about any resource availability, okay? It just sends the data, no acknowledgement. The UDP header consists of 8 bytes, 64 bits, source port 16, destination 16, length, and then checksum, okay? And this checksum is not responsible for acknowledgement, okay? This is just a 16-bit field used for error checking of the datagram header and data, okay? It just checks whether there is any error. It's not for sending acknowledgement. So with regards to UDP, we have got our DHCP, which is your dynamic host configuration protocol, which gives automatic IP addresses, can be IP version 4 or IP version 6, as we will look later. Part of your DNS works with your UDP. Okay, when you want to access a server, you do not type the IP address, IP version 6 address or IP version 4 address. You type www.netacad.com, okay, or www.cisco.com. That is the translation service that we have, okay? That works on UDP because it needs to be fast, okay? SNMP, TFTP, voice over IP, video conferencing, all of these, okay, they need to work on your UDP. Now, another aspect that we should know about your transport layer are port numbers, okay, which are both on TCP as well as your UDP, okay. So the TCP and UDP transport layer protocols, both of them use port numbers. Why? Because when you access a server by using UDP or TCP, you are not accessing just one service. You are accessing multiple services. That is why each application service will be on a different port, okay? So you have to have a source port number and a destination port number, okay? If you're accessing a server or a remote host, you mention that, yes, I'm accessing this service, and this is the port that I'm coming from, and this is the port that I want to access. Another application will access the same server, but using a different port, okay? For example, the most famous port, 80, that means you are trying to access a page, a HTTP page, okay? An example over here. There, a client and a server, okay? Now the client is accessing, coming from a source port 1304, okay? And it's trying to access perhaps a FTP service. Now, coming from source port 1304, and the FTP service on the server is on port 21. It's also doing another access coming from web client 1099 and it's trying to access port 80. That means it's going to be a HTTP access. Okay. Now, using just the same connection, you can have two different services distinguished by the different port numbers. Okay. So the server will allow your client to access, okay, through different ports. Okay. Another thing you should remember that the combination of the source port and the destination port, okay, is known as socket. Okay. If you have experience in Java we have got something known as socket programming. Okay. So when you say what is a socket, it's a combination, okay, of your source and destination port numbers. Okay. Why do we need sockets? Sockets enable multiple processes running on a client, okay, to distinguish themselves from each other. Similarly, on the server, how do you distinguish between FTP and your web server HTTP requests? Very simple, by using different port numbers, okay? And there is a series of port numbers, okay, that have been established. These, for example, 0 to 1023, if you remember, we studied this in a lecture. These are the well-defined port numbers which are reserved. We cannot change them. We also have registered ports that we can register by going through IANA, okay, that is starting from 1024 to 49,151. We also have private or dynamic ports, okay. These private ports are actually also known as ephemeral ports, okay, and it depends on which application you're using. You can register and use these ports, these private ports. Now, what about the ports from 0 to 1023? Now, the most famous of them, okay, and which protocol they use and what they are. For example, 20 is always for file transfer protocol to send and receive data. But before you establish 20, you first have to establish 21. That means you establish the control, the connection. Okay. SSH is your secure shell, ensuring that your data that you send is encrypted so that people cannot just read it. Okay. 23 is your telnet. Okay. Telnet will not be encrypted. That's why we need SSH. 25 would be your SMTP. 53 is your DNS, which is using both UDP and TCP protocol. Okay, DHCP is your working on your UDP protocol. Remember, DHCP server is used to assign IP address automatically, or even a router can be configured to be your DHCP device. Okay. You also have your client which requests access to a DHCP IP address. Okay, so when it's requesting, it will be working on port number 68. Okay, and the server will be giving, will be assigning an IP address based on that request on port number 67. Okay. We also have trivial file transfer protocol, TFTP. We also have our famous HTTP, which works on port number 80. Okay, so these are some of the ports which are well known. Okay, you can get details, okay, about your network, about your connection, okay, your client connection by using the netstat command. Okay. It even tells you information about unexplained TCP connections that you have. If someone is trying to access your network, okay? So NetStat is an important tool. It troubleshoots network performance by measuring the amount of traffic on the network, okay? If you have a slow speed on your network, it tries and finds out what is the reason. It identifies what software is running on your device and which software is using that internet connection on your device. Okay, it gives you all those details. Okay? You just have to understand the concept of NetStat, the details. How can you know that which IP address and on which port, okay, if the connection has been established, okay, which one is it using? For example, here we can see that the foreign address that's trying to access the connection is HTTP. Okay, so this is one way you can actually troubleshoot and diagnose your slow network speeds. Okay, you will learn more about this NetStat in CCNA 2 and 3. Moving on to TCP communication processes. So when you are trying to do a TCP communication, let's say a client tries to access a server, okay? When it's a TCP connection, remember, coming from a client, you are accessing, both of them, let's say they are accessing the same server. The server can actually give access to both this client as long as it has got its services on different ports, okay? So the server knows that its HTTP response is on port 80. And let's say its SMTP response is on port 25. So if this client is coming from, let's say, port 51152, and it needs 25, port 25, which is your SMTP response, okay? The server can give request to that client. At the same time, the server can also serve your client one, which is trying to perhaps get a web page. It's on port 80. So this server can work different applications as long as they work on different ports, okay? So that's why you have to make sure that you do not have the same port numbers, okay? So it's important we go through this. Any incoming client request addressed to the correct socket is accepted. What is the correct socket? The correct socket is the source port and the destination port, as we read earlier, okay? And then the data can be transferred. So when you want to have a TCP connection establishment, again, they are repeating what we studied in the lecture. It's a three-step handshake, okay? First, your client will initiate, okay, a request, okay? So it will send a SYN, okay? And let's say the recipient will receive the SYN, and then it will send the acknowledgement for that SYN, okay? And then if, let's say, the sequence for that acknowledgement is 300, then the client will acknowledge that sequence, okay? And then after this three-step handshake, you can start exchanging data. Very simple, okay? This is how TCP connection is established. If you want to terminate the connection, very simple, okay? Send the FIN flag, okay, to your destination. Once it receives the FIN flag, it will send an acknowledgement for this, and it will also send its own FIN flag, And then the client will send another acknowledgement for this, and then the connection is terminated. Okay. So the three-way handshake, it ensures that the destination device is present on the network. If it's not a network, then you cannot do the connection in the first place. It also ensures that the destination has an active service and it can access that request on a specific port number. Okay. It also informs the destination that the client is intending to establish a communication on a specific port number. Okay. So that's why we need a three-way handshake. Now, in three-way handshake, there are some control flags. Okay, remember the flags that we went through? Some of these flags are, for example, FIN flag and so on. Let's have a look. These flags are urgent, acknowledgement, push, reset, SYN, and FIN. Okay, these are nothing new, my dear students. You have studied already in your lecture session. Okay, these flags are all inside your control bits. Okay, and depending on the bit number, it can either be urgent, act, push, reset, SYN, or FIN. Okay, there is a number associated with each of these flags. Okay, for example, if it sends a RST flag, it will reset the connection. Okay, FIN, that means we are going to close the connection. Next, let's look at reliability and flow control. Because your transport layer is also responsible for your flow control. If you remember our lecture session, sometimes the client will be sending at a higher speed and the receiving computer may not be able to absorb if there is a bottleneck, as we studied. In those situations, what it can do is it can control, the transport layer can control and send an information that slow down. Okay. So that's the whole idea of TCP reliability, ensuring that data is sent in order and delivered. Okay. When you send your segments, it may not be in proper order. But what does it do is TCP will reorder it. Okay. So that the recipient will get it in a proper sequence. In case of reliability, okay, one way is when the segments are sent, okay, it sends an acknowledgement with regards to those segments. Okay. For example, if there is an issue with your segment 3 and 4, okay, then perhaps it will send an acknowledgement telling you that you have to perhaps resend segment 3 and 4. Okay. So you get your segment 1 and segment 2, you get an acknowledgement about all the other segments that, hey, I have perhaps not received 3 and 4. Unfortunately, when you do something like that, it will send segment 3 and 4 again. But the successful segments from 5 to 10 will also be sent. Okay, you're using TCP, remember? So duplicate segments can be an issue. Okay, so that will slow down your network. It will retransmit the segments. Okay, now there is a way to get beyond this and to solve this problem. Okay, because if you get an acknowledgement and you have to send again from 3 to 10, we are creating duplicates and you're creating issues. So one way of solving this is by having, instead of an acknowledgement, instead of sending an acknowledgement, what you do is you send a selective acknowledgement. Okay, so just like the previous one, okay, 3 and 4 have issue. Okay, so you send a selective acknowledgement and say that, hey, I have received 5 to 10. You see, I have received 5 to 10. This is my selective acknowledgement. So the issue is between 3 and 4. So it will send 3 and 4 and then the rest. Get an idea? So this selective acknowledgement, you have to make sure that both the sender and the receiver support this. Okay? And this will ensure that there is no duplication when you have got a selective acknowledgement in play. If you remember, we studied this in a lecture, but in detail. When it comes to flow control, whereby the receiving computer will set the pace, okay? It will set the pace and say, hey, slow down, or you can send more, okay? This is also controlled by your TCP, okay? What it does is, it will send the maximum window size. Remember, we studied this in the lecture, sliding window, okay? And it will have also a maximum segment size. It will send this to the sender. Based on this, it will see that the window size is 10,000, maximum segment size is 1460, and then it will start sending the data. And once the acknowledgement for that has been received, it will keep on sending the next sequence. Okay. And once the window size has been exhausted, it will send another window size. Okay. So if there is a bottleneck at the recipient, then perhaps it will decrease the window size, and it can also decrease the maximum segment size. Okay. So this maximum segment size actually is usually 1,500 bytes. Okay. But remember, if you look at your TCP header, if you look at it, it has got 20 bytes for the IP version 4 header and 20 bytes for the TCP header. So if you take that into consideration and take the difference from 1,500, then you will have 1,460. Okay, so the math checks out. If there is a congestion, okay, if there is a bottleneck, okay, remember at the receiving end, if something like that happens, then what happens is you get an acknowledgement for certain segments, okay, and based on that acknowledgement, let's say the acknowledgement says that I have received 1 but not 2, and then it will again send your 2 and 3. If you're sending a selective acknowledgement and setting the pace, then it will only send 2 and 3, it won't send 4 anymore. Okay. What about UDP? In case of UDP, there is no such thing as establishing connection. Okay. That is why UDP is low overhead. Okay. It sends data without establishing any connection. Okay. It also does not track sequences, and if one part of your segment is missing, tough luck. It doesn't care. Okay. So let's say if you have got 6 datagrams and let's say 3 is missing, and they come garbled and not in order. Okay. They are not reordered. Data is just received, and this ensures that speed, okay, is guaranteed. UDP-based server applications are assigned to well-known or registered certain registered ports. For example, if you have a DNS request, okay, you're using access to a server asking for a DNS resolution. That means you are typing www.cisco.com, but we know that routers don't understand that. Okay, so it will go to a DNS server and it will find a relevant IP version 4 or IP version 6 address and then forward your request. Okay, or another protocol is your radius protocol. Okay, if you're using a dial-in modem to access a remote service, you're using a radius protocol. Again, for radius, you have to use a UDP connection. Okay. Again, when you do a DNS or a radius connection by using UDP, yes, it will be working on different ports. For example, over here, your connection, your UDP connection for DNS will be on port 53. Let's say your radius will be on port 1812 and so on. So based on the different ports, your server can also generate UDP requests. Okay, so this server on port 53, it will give DNS request for client 1 because it accessed your server 1 and was trying to resolve a DNS name to IP address. Okay, the same goes for the same server also generating a request for your radius on port, let's say 1812 and so on. Okay, just like your TCP, your UDP also works on different ports, and based on that ports, it can generate the requests from the client. Okay, so that brings us to the end of our transport layer. Okay, anyone has any questions in particular with regards to today's session, transport layer?
None so far.
Okay. What we have studied here is sort of a summary of what we did in the lecture. If you remember in the lecture, we went into details. Okay. Here we are just studying a little bit on the surface knowledge rather than going into details. Okay. So that brings us to the end of this session. Thank you for your attention.